k equal 1. So we have t prime over t is equal to then square root of L prime over L. And so a nice example of that, a uniform force field, what's the usual uniform force field that we are used to writing down problems in? Well, the constant gravity, things falling under gravity. And therefore, we can say that the fall time goes as the square root of the initial altitude, right? Without solving any equations. So another example is in the case of, I'm running out of board space. What am I going to erase? I'll put it in over here. Is in the case of, say, gravity or Coulomb attraction. So we have k is equal to -1. And in that case, then t prime over t is equal to L prime over L to the 3/2. So do you see what we just got? We just got Kepler's third law. Pull it like a rabbit out of the hat.
How did they figure out which K to choose?
Well, which K to choose? Who figure out?
Landau, yes.
Or
Did they just?
Newton or
did he just try out? Well, let's let K equal 2 and.
No, K. I mean, we chose K because that is the function.
Oh, right. Okay, right. That was the degrees.
Right. So that says for K equal -1, this is going. The potential is going as 1 over R.
That's right. Okay.
So if K is -1.
So if we did K equals -2, we're talking about 1 over R squared system.
In the potential. So a 1 over R cubed in the force.
Oh, okay, okay.
Remember, we're talking potential, not force.
And 1 over R cubed is not really a system we know.
Not that it's not a system we know,
but it's a solvable system.
Solvable, although unstable system. So then the last application, what the hell are they doing?
Big termites.
So the last one, example of this is the virial theorem. So let's see if I can get this one straight. Right, so this is, well, okay. So the virial theorem involves averaging quantities over the system over some time and space and saying what the averages of T and U are. And so I'm just going to erase a bunch of this. Just give me a little room. So we start with that t is a quadratic function of the velocities. So that by Euler's theorem, and sort of obviously, if we write down that sigma VA dot dt dVA is equal to 2t. So if it's a function that the 2 drops out there. And dt dVA is equal to PA. So we have 2t is equal to sigma PA dot VA is equal to d dt. And so now we just played we're just doing the chain rule backwards. It's like completing this. Sigma A PA dot RA minus sigma RA dot P dot A. And now let's do time average of this. So if you do the time average of any function f of t, as long as it converges and is bounded, then the time average is going to be 0. Well, if it ain't running away, right? And I integrate long enough.
Oh yeah, sure.
Yes? So, in fact, Landau makes a little bit of a side story out of it that I think is fairly straightforward. So if we're going to do time averaging now, space. So we wind up with 2t bar is equal to the time average of A R A dot grad U and bar over this to indicate time average. If the potential energy is a homogeneous function, once again, of degree k in the radius vectors, then you see what happens immediately then, that this pops out to be 2t bar is equal to k u bar. And when I put in, well, that's the nice result. But,
No, this is from Landau.
So let's see. However you want to write this. Well, you can also write this as T bar plus U bar is equal to E bar, and E bar is equal to E for a conserved system. So we can write then that, sorry, I'm wandering all over the board. We can write that U bar is equal to 2E over K plus 2. And T bar is equal to KE over K plus 2. So all the time here we have been keeping loose the, we haven't specified that we're dealing with Newtonian gravity or whatever. This is for a general homogeneous function over K. For the small oscillations case, for example, when we put in K equal 2, you see that T bar is equal to that T bar is equal to U bar for the small oscillations case, right? So we get 2 over 4 both cases. And for the Newtonian case, which is where people are generally talking about the virial theorem, we have K equal -1, and we have that 2T bar is equal to minus U bar. That is, and E is equal to minus T bar. This is the in accordance with it, the interaction takes place in a finite region of space, and that the orbits are contained, the energy is negative. So we popped out the virial theorem with more of this very general hand waving, which I find to be, maybe this is the sort of thing when you get to be an older physicist, you find these things, these aesthetic things, to be more lovely. And as a young punk, I was more interested in solving problems.
This doesn't give you a very solid belief that it's true. It just makes it seem like it just kind of happens that way.
By smoke and mirrors, right?
Yeah.
So
there's not a lot of conviction in showing it this way. It just makes for a shorter.
Well, there is conviction in, because if we go back and assume and examine the assumptions that we had to make, and what I like about it is that you see that this is stuff, these consequences are hanging on some very general assumptions.
Yeah.
And, but there are things that sneak in that are not obvious all along in this business, and you have to keep your eyes open if you care. If you just want to solve problems, that's one thing. But if you're trying to think about where in the world does all of this stuff come from? For example, we talked about that there are these constants of motion, the integral constants of motion, the 7 of them. And one of them is energy. We all go, oh yeah, energy, cool. So would any of you care to tell me what energy really is? Have you ever thought about that? We all think we know what energy is. What is energy?
It's this stuff that floats around and has magical properties.
Right.
You mean something like a metaphor?
Some of these things you think very hard about and they'll make your head hurt. What?
Were you talking about like some kind of physical description of it, or just
Right.
like that's related to the momentum?
Well, no, I'm talking about in some kind of bigger picture. What does energy mean? Energy has, we can say kinetic energy, oh yeah, 1/2 mv squared, yeah, we all understand that. But we all have this idea that the mass energy of the universe should be conserved. Probably. If not, where does it go? But what the hell do we really mean by energy? And people who think hard about general relativity worry about, in fact, just that issue. There are a lot of these things that we assume we have intuitive understanding of, but when you get right down to it, a person popping in from another universe or somewhere, it might not be so obvious to them. Yeah.
I was just going to say, like, throw out something that I thought maybe energy could be. I think it might be something that's just very interesting to count and keep track of, sort of thing.
Well, it's kind of a unit measuring the magnitude of an interaction.
Right. And one can define it in various of these terms, but the rubber hits the road when we start thinking on some of these grander terms about the cosmic energy that we don't know what it is. We don't have any real idea of what it is. We have an idea in terms of what it does to the equations and cosmology, the dark energy. But nobody really knows what the dark energy is.
Goes to Landau's stat mech. He talks about this, how you would think the universe would be in equilibrium, but you know, if we look at it, it seems not to be. It's expanding, and there's energy flowing everywhere, and it's very strange.
Yeah.
We're going over his
Yeah.
physical mechanics book and with Chester Boss's class.
Yeah. Geez, I should get a copy of that. I always liked stat mech. I've never taught grad stat mech. But
Yeah, I just have it might be a silly question, but like, pondering the significance of like energy as we are, couldn't we do the same thing like with other physical quantities?
oh yes, definitely. Definitely. I mean, the worst one of all that has bent many people's minds is when you start studying quantum mechanics. And there's the wave function. Like, what's this wave? What is this wave doing? Oh, it's what you square and then you get a probability. What is this wave? Well, you don't know what the hell it is. So.
That's comforting.
But these things work, and so the bottom line for when you're talking to your pragmatic friends is say, screw you, I don't care. It works. I can make predictions. Let's see you psychologists make some predictions, or you folks who believe in relativity of intellectual relativity, the emergence of knowledge as a social construct, that kind of thing, that nonsense, which is dying out across campus.
What was that?
The emergence of knowledge
As part of
cultural. I don't
It's
know.
like
Science is
part of
science is a social construct. There are people who have been very strong on that. I know some of those people.
who don't care at all about predictive value.
Pretty much, yeah.
Okay.
So I say to any of those people who think that Newton's law is a social construct, that please step out of my window and let's see if Newton's laws are working.
Let's go to somewhere with a radically different culture and step out of a window there.
Yeah, right, exactly. And the postmodernists, you guys don't know about probably about all these, the intellectual wars with the postmodernists who are on the retreat nowadays, thank goodness. But these people have some, to my view, very dangerous anti-science attitudes. And we could spend obviously the whole class talking about the philosophy of science, but I'll just lay my interpretation on you for your consideration, which is, if you think about these things hard, you're going to wind up getting a headache. But if you think these laws of science are absolute magic laws, that who knows where they came from. Mr. Goldstein suggests that God gave them to us, if you translate his Hebraic phrase. But wherever they came from, I don't really care. I argue that we're a bunch of hackers who make approximations to what we see as our physical reality. These things are not laws; they're principles that work pretty well. And the lesson that you will see as you proceed through physics is that as you make better and better approximations, things get better. But like the most blatant examples, say the hydrogen atom starts out this really easy thing. Bohr orbits, clean, simple, and then we get the wave functions and they're harmonics, and then we have start having little complexities like the splitting of the energy of the various angular momentum states and all of this, and then we have some spin orbit coupling, and we get better and better approximations. You look at the spectra more and more finely, eventually you see even relativistic corrections to the lines and so on. So it's a series of approximations. Everything we do is just a house of better and better approximations. And none of it is perfect, but the truth is that for most circumstances, we can do pretty well. Some things have not been easily yielding to that, like in turbulence and hydrodynamics and so on, but people are starting to deal with chaos. But we at least now have an understanding with sensitivity to initial conditions, SIC, which you'll hear people talk about, and if we get into the chaos chapter, we'll get to talk a bit about. But it's there in these systems, and not only do we know that there are systems where our predictions are not worth crap, but that we can predict that they're not worth crap, which is a good thing, because we can see that there's this instability in lots of nonlinear systems. We're talking about the simple harmonic oscillator. If you just perturb it a little bit, you're going to get into some big trouble. For instance, the driven damped oscillator easily leads to chaos. Just to crank up the driving term a little bit and so on, you can get it into chaotic motion. And not only we can say that we can't predict the location many cycles in the future, but we can say when things are going to turn bad. So that's progress. So I've wandered aside, but these are things that you should have seeds to cogitate on as you go along. That we're really just a bunch of hackers, and some of the hacks are much better than other hacks. And one of the greatest hacks of all time is conservation of energy. Conservation of energy just bloody works. Everywhere we can look at it, it seems to work. That you can cheat Mother Nature in lots of ways, but one thing you cannot, nobody's figured out a way to cheat Mother Nature on is conservation of the energy of the system.
Unless you do it for a short amount of time in quantum mechanics.
Exactly, but you don't get to keep the profits.
Right, because over a time average, it's just gonna...
Is gone, right. So, you know, that's part of why physics is such a fun business. It's so very beautiful, but we're always struggling with these peculiar boundaries, and with, you know, in the end, what physics is, we're playing a game. When you're on the research fund, you're playing a game that you don't know what the game is. Nobody's told you the rules. Nobody's even told you if it's possible to win. We've been winning for a couple of centuries now, but people struggle with, we have the standard model of particle physics, which seems to not be in conflict with much of anything except for a couple of little cracks. But we have this standard model, so everybody in the particle phys biz would like to have a unified model that puts the strong and weak and so on interactions all together into one theory. Can we indeed find such a theory? Is it necessary? No, it's not necessary. God did not come down and say, boys and girls, just get your act together, you'll get the weak, strong, and electromagnetic and so on theories. That's it. Or that there is a unified theory out there. If you work hard enough, or tricky enough, you will get it. We don't know. Maybe that's it. Maybe we're at the end of the line.
It's kind of like Feynman was too. Feynman was always, it doesn't have to make sense. We're just trying to figure out how it works, not why.
Exactly. And I'm always participating in proposals, for instance, about the neutrino biz, where we've made some marvelous discoveries in the last few years, and some really interesting stuff about these damn neutrinos. And so we all write proposals about the exciting future of neutrino physics, but it's total